Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. Welcome back to these piecewise defined continuous functions. And this is the expressions which I wrote in my last class. They're still there. And we were talking about the one-dimensional problem here of second order differential equation. And then I also wrote down here the weighted residual statement of weak form. So we discussed in the last class in very great detail how the function phi hat can be expressed as a piecewise continuous functions, number one. Number two, how the coefficients of the functions are rewritten in terms of nodal values. So that way, we are satisfying the C0 continuity of the approximation function at the element boundaries. So that way, this is what we have derived last time, is that phi hat, the approximation, now can be written as this n1, 1, phi 1, and this, and if you look at this one, this is n1, phi 1, n2, phi 2, n3, phi 3, n4, phi 4. Just to recall, this phi 1, phi 2, phi 3, phi 4 are equivalent to our coefficients b's, and then this n1, n2, n3, n4 are equivalent to our psi 1, psi 2, psi 3, psi 4. Okay, so these are psi 1, psi 2, psi 3, psi 4, and phi 1, phi 2, phi 3, phi 4 are the coefficients b's. And we studied in detail. So what will be this? So this n1 or psi 1 is defined over domain 1, and n2 is defined over omega 1 and omega 2. It has these expressions, okay, and then 0 everywhere else. So that is again is the beauty of these finite element approximations, okay. And so similarly, n3 is non-zero on domain 2 and domain 3, and in particular, this has a value of 1 at node 3. So all these shape functions have the property that they are equal to a value of 1 at that particular node and 0 everywhere else. Okay, this is how the shape functions are equivalently sized. Okay, coming back to this problem, let's go back to this problem. So what is that? So which we are doing here. So there are here the boundary conditions on the function itself, function phi is equal to phi a and phi b at x is equal to 0 and x is equal to, 1. And so looking at this expression, if this is the expression for phi hat, so phi hat is given as n1 phi 1, n2 phi 2, and n3 phi 3. So this is the finite element approximation of the approximation phi hat. And then if we want to apply this boundary condition, phi is equal to phi a at x is equal to 0. So if you want to put x is equal to 0 in this expression, what is that? It's going to be, so what is the value of various functions n1, n2, n3? So phi hat at x is equal to 0, let's say, or x is equal to x1. So if this is what we want to evaluate, so if you look at these expressions n1, n2, n3, n4 as depicted here, what is their values at x is equal to 0? At x is equal to 0, so n1 has a value of 1 here, and n2 has a value of 0 and n3 has a value of 0 as well as n4 has a value of 0. So essentially this is value of 1 and this is phi 1 itself, right? Everything else n2, n3, n4 are 0. So that is the beauty of these shape functions. And so this is equal to phi a. So similarly, the other boundary condition at x is equal to 1 is, you can see at x is equal to 1. So this is what x is equal to 1 is. And at this node 4, so you can see that n1 is 0, n2 is 0, n3 is 0, but n4 is 1. Okay. So all these three are 0, so leading to 1 on phi 4 itself. So which is equal to phi b. Okay. So phi 1 and phi 4 are equal to phi a and phi b, which are defined for us. Okay. We'll put a bar there. So that means that now the approximation is nothing but phi a and 2 phi 2 and 3 phi 3 and phi b. Okay, so this is, so what we have here, phi a and phi b, if they are given to us, so the rest of the expressions is known except they are now phi 2 and phi 3. So now we have the whole expression, whole approximation here is just having two unknown terms here, phi 2 and phi 3. So these are the, obviously the nodal values at 2 and 3. So this is, so the unknowns here are 2 here, phi 2 and phi, right? So this is what we have to solve for. So now let's look at, so we go back to this expression and then we derive two equations. And what are the two equations which we are going to derive here? So what is the Wi which has to be taken here? What is Wi which need to be taken here? Okay, Wi need to be taken here is, can we take, if you call this as psi 1, psi 2, psi 3, psi 4, can we take psi 1? So the two equations we need to get here, can we take Wi to be psi 1? That means that equivalently n1. This is the question here. Psi 1 is equivalent to n1. So psi 1 is what we were used to. And can we take Wi to be equal to psi 1, which is equal to n1 here? So it is not possible to take these Wi is equal to psi 1, what is, or n1 for that matter, because what is the condition on psi 1? So psi 1, if you recall, has to be, the W has to be 0, W has to be 0 at the boundary, on the gamma phi boundary, the weighting function has to be 0. So that's what we said. And the weighting function Wi has to be 0 on gamma phi, that's for 2 dimensions, or the boundary, let us say x is equal to 0, as well as, I can as well say it right now, where phi hat or phi is prescribed. So wherever we have the prescription of phi hat here, there, those weighting functions only can be taken where the weighting function has a value of 0 here. So if that is the restriction, okay, then what are the tries, or for that matter n's, which we can take here? So out of this n1, n2, n3, and of course n4 here, which are the weighting functions or the shape functions we can use as weighting functions? Okay, can you tell me? So the thing here is that if you take n1, then the value of n1 is 1. So that means that this weighting function is not acceptable, right? So that means that you can choose n2, which has a value of 0 here. We can choose n3, which has a value of 0, as well as, since this also is prescribed function on phi, so at 4 also we need the weighting function to be 0. So that means that it should be 0 here. And so the n4 can also be not used. Okay. So the two weighting functions that can be, or those can be used are n2 and n3 only. So n1 and n4 have, as a further explanation, n1 and n4 have value 1 at x is equal to 0 or x is equal to 1. Okay, so I just wrote a further explanation saying that n2 and n3 can only be used, n1 and n4 cannot be used here, because n1 has a value of 1 at x is equal to 0, n4 has a value of 1 at x is equal to x is equal to 1. So thus we have decided what should be the weighting functions here. So let us taking, so these are the two equations which we develop, and then using those two algebraic equations, so we should be able to solve for the unknown value phi 2 and phi 3. So let us just say wi is equal to n2. Then the expression, or the weak form of the weighting function is what? So I'll write it here. So it is dn2 by dx, and here d phi hat by dx, and n2 times phi hat okay. So here we are using wi is equal to n2. A similar expression we'll also write it for wi is equal to n3. So for the moment, so let's explore what happens to wi is equal to n2. Okay, so then, so this is phi hat has been given here. So now dn2 by dx. So this is d dx of n1 by 1 Okay, so this is the equation, and of course phi 1 and phi 4 are given to be phi a and phi b. So just remember, I'm just putting a bar here. So they are defined values phi 1, phi 4 as phi a, phi b. So just keep switching from phi a, phi b or phi 1, phi 4. So it's equally okay. So now, so the thing here is that now I wrote the integral between 0 to 1. So none of these things are fully defined over the complete domain. They are piecewise defined continuous functions. So if you take a derivative, so you should be careful. Okay, so this can be written as omega 1, the whole thing, and whole thing omega 2, or if you want, we can write it as x1 to x2, x2 to x3, x3 to the whole thing has to be repeated. So because the total domain 0 to 1 has to be split up into 4 subdomains, 4 elements, because these expressions n1, n2, n3, n4 have different expressions in each subdomain. So whenever you use the integrations here, so you have to appropriately use these things as defined in each element. Okay, so then we have to write it here. So these have different. So that means that omega 1, omega 2, omega 3. So in fact, this, if you do this here, x1 to x2, these become longer and longer expressions, but it doesn't matter. So they look long, but once we simplify them, many of them will turn out to be 0. So this is between x1 to x2, right? I completely wrote it. And similarly thing you have to write it for x2 to x3. So I'm not repeating, I just wrote one expression. So the same things will be repeated here. But only thing here, when you talk about the domain omega 1 here, so n2, so since now that we are having expressions, so n2 should be as defined in 1. So all these things as defined in 1. Okay. Understand? So similarly here, so when you write it x2 to x3, so then all these things will take the expressions as defined in 2. Okay. So this is, that means that the expressions will become slightly longish. Another very important thing which you should observe here is that these things are happening as the products here. So then it's a product of d dx of n2 here, because we are taking psi wi to be n2, and multiplied with a similar one of n1, n2, n3, n4, and so similarly here. So the same thing here. Okay, right? So one thing you can observe here is that this becomes non-zero only when both n2 as well as all these things are non-zero only. Okay, both of them have to be non-zero. If any one of them is 0, so then that integral will be 0. Okay, so that is the beauty of this one. So these n1, n2, n3, n4 are defined compactly, and they are non-zero only on some terms. So let us see, for example, here, if you are looking at the first expression here, for this is the x1 to x1, x1 to x2, and this is the element 1. And out of these many expressions here, so what is that where both of them are non-zero? So n2 of 1 here, so this is n2 of 1, all right, this is non-zero in element 1, right, element 1. And what else will be non-zero here? Okay, so if you look here in the domain 1 here, only n1 is defined to be non-zero, while n3 is 0 here. So this will turn out to be simply, so out of these expressions, so if you write x1 to x2 and just write what are non-zero, so it is dn to dx by 1, so this is the domain. And the only other thing that non-zero is this times phi 1, that's all, right? So this is the only one here. And so similarly here, there is an expression which is, there is also one more here, which is non-zero here. n2 is also non-zero, obviously. So I will write dn2 by dx and dn2 by dx of zone 1, and this is I2, right? Right, so this is that. And in the second one, it is n2 of 1, and out of this one here, only n1 and are non-zero. So like this. Okay, so this is zone 1. What about zone 2? If you go to the zone 2 here, so that is x2 to x3. So if you go to second domain here, so here the only thing that is non-zero here is n2 will be non-zero, so that is there. And together with that, obviously we have n2 itself. In the domain 2, so we have again a n1 will not be there, so there is only n2. This is phi 2, and what is the other one? n3 also will be there. And similarly, we have okay, coming to this third one, x3 to x4. If you look at the x4, this is the third domain. If you look at the third domain, so n2 is what happens? n2 is 0 here. The first part is 0 here. So that means if that is 0, and then so that means that it is 0 here. Okay. So the contributions are coming only on the element 1 and element 2. So this is the two non-zero things are coming here. Okay, so this is how we have to decide. So that means that we have to find out the integrals here of various quantity. So let us just look at this one. So they're repetitive in nature here. And let us just derive a very general expression, because either it has this or this nature, or this, both have the same kind of expression. So let us just do it. Let us take just xi, a general approach here, approach for integration. Let us do this. This is, we call it as Ni, and Nj. Okay. So what we have here, the expression for Ni, this is for element E, all these things. If you have some other element, so you'll have another expression. So here we have xj minus x. And similarly, the expression for j okay, so this is how it is. Now let's look at the various combinations of this one. So here we have combination of n2, n1, n2, n2, and n1, n2, and all those things. So now let's look at the expressions here. So let's look at a general expression, dni by dx, dnj by dx. Let's look at this. This is what's being repeated here. Okay, so this is for element E. So this will, let's call this as Kij of E. So in fact, this I and J can be general. Both can be II, both can be JJ, both can be IJ and JI. So there are, all combinations are possible. For example, if you talk about 1 and 2, so this Kij can be 1, 1, 2, 1, 1, 2, and 2, 2. All possible combinations are possible, because you can take N2 here, N1 here, N1 here, N2 here, and on and on. So different combinations are possible. So we are trying to generalize it to get the expressions here. Okay, so for simplicity, let us just take xj minus xi to be some value h here. And then what happens here is that, let us say, take this one. Then let us take kii for the element, a general element here is, so here dni by dx, ni. So then this will be, if you take a derivative here, the denominator is h, and then there's a minus x, so it is minus 1 by h, and again a repetition, and then we have here xj minus x divided by h and square. Okay, so if you take this one, so then we have, you can simplify this one. I'll just leave the integration to you. So it's 1 by h plus h by 3. So what we are assuming that h here is xj minus xi. Okay. So this is kii, and then so similarly we have kij, in which case we have, okay, I'll write it dni by So this will turn out to be minus 1 by h, and this dnj by dx will turn out to be plus 1 by h, and this is two expressions, xj minus x by so I leave the derivation of this one. So it is minus 1 by h first one, and h by 6 is the second term. Okay. So like this we have kii, ij and ji, jj. So kjj is the same as, kji is the same as kij, and kii ki. So this is in a nutshell for a general domain integral here. So this is, there are xi, xj. So it can be I by maybe 1, this may be 2, this is 2, this is 3, and so on. So this is how we evaluate. And then this is the 4 terms which you get to be the integrals here, ii, ij, ji is the same as ij, and jj can be same as ii. And then we'll stop here for the moment. So we have calculated the equations related to a general element, and these things which we had to put here, and then we'll simplify the overall system equations. Okay, we'll stop here for the moment, and then we'll continue this one in our next class. Bye bye.